Hey guys, Dr. B here. This is topic 1.7, periodic trends. The objective is to be able to explain the relationship between trends and atomic properties of elements, electronic structure, and periodicity. The periodic table is arranged from the lowest atomic number of protons, to the highest. The blocks of the periodic table correspond to the s,p,d,f groups of the electron configuration. Remember the s block, p block, d block, f block, and how they're arranged, etc. The number of blocks, so let's say, for example, let's look at the 4s2 block. So 4s block, if we are going to be counting 1, 2, etc., if we're on that 4s2, that means there's 2 electrons in that particular block, etc. So we went over electron configuration, so you should be able to remember that. Elements that have the same valence electron configuration tend to have similar chemical properties. So you may see a question that's going to say, based on this, let's see, maybe it may say like an element is found to have 7 valence electrons and 2 orbitals, for something like that. Which element is most likely to behave the same way or have similar chemical properties, something like that. Most, if not all, periodic trends can be explained by the arrangement of the electrons and the number of protons in the atoms, and you're applying Coulomb's law. Like I've said, Coulomb's law is going to be important, and if you see a question that has something about that, you're going to want to really, really, really know it. And if you really, really, really know it, get it right, some good points down there. Excuse me. So key terms: Coulombic attraction. So it sounds fancy, and you use it correctly, shows you really know what you're talking about. Electrostatic attraction. So the positive negative attraction which take place between two charged particles in close proximity. It increases when you increase charge, and Coulombic attraction, or this interaction, will increase when you decrease the distance between particles. So remember, you're using Coulomb's law, not mathematically, but qualitatively. When discussing periodic trends, the charged particles are the nucleus and the electrons. And we tend to use the outermost electrons or the valence electrons when we're talking about this. Coulomb's law states that the attraction between two charged particles is proportional to the magnitude of the charge and inversely proportional to the distance between them. To make this simpler, larger the charge, more attractive forces; further away, increase the distance, you decrease the attraction. Effective nuclear charge and electron shielding. The effective nuclear charge is the net positive charge experienced by valence electrons. It can be approximated with the equation below. So effective nuclear charge equals the atomic number minus the number of electrons and orbitals that are closer to the nucleus. The shell model. It describes the arrangement of electrons within an atom as described by the electron configuration from the Aufbau principle. The first shell is closest to the nucleus and would have the greatest Coulombic attraction for the nucleus since it's the closest. And there are no electrons that are shielding the nucleus. Shielding means it's kind of decreasing the attraction. The subsequent shells, which overlap and have lower Coulombic attractions due to the greater distance from the nucleus, they decrease in effective nuclear charge because the innermost electrons kind of shield it or kind of prevent it from being fully attracted to it. Periodic trends. So first, ionization energy. It is the energy required to remove the outermost electron, or the highest energy electrons, from a neutral atom in its ground state. This first ionization energy, it decreases as you move down a group. Electrons are further from the nucleus and therefore have a lower Coulombic attraction. Additionally, the inner shells of electrons shield or block the proton's force of attraction. This results in the outer electrons being easier to remove. First ionization energy increases as you move across a period from left to right. We've talked about this sophomore year. As you move across the period, the atomic radius is smaller, and there is an increase in the number of protons in the nucleus. Both factors result in greater Coulombic attraction, which in turn means that it will require more energy to remove the first electron. There are a few places where this does not follow the trend, and you can see on this graph by here, or right next to it, I'm sorry, that there's kind of a weird drop between beryllium and boron and nitrogen and oxygen. So why is that the case? We kind of alluded to this a little bit sophomore year because some people noticed that in the graph. So when you go from Be, so beryllium, to boron, when the first electron is removed from boron, the electron is being removed from the 2p orbital. Since this orbital is further away from the nucleus, it takes less energy to remove it, even though there are more protons in the atom. Nitrogen and oxygen, this is an exception, like beryllium and boron. When the first electron is removed from oxygen, it takes less energy despite the increased number of protons because the electrons in oxygen are sharing the 2p orbital and therefore have greater electron-to-electron repulsions, making it easier to remove one electron. The second ionization energy is the energy required to remove a second electron from the atom, and so on for each electron. You're going to be given, sometimes you're going to be given a chart that shows, like you see on the right, different ionization energy numbers and the enthalpy, the kilojoules per mole, basically how much it takes to remove the electron. So you'll notice, remember we said that the ionization energy number, or that energy, is referring to the removing of valence electrons, or the outermost high energy electrons. So if it's a higher energy, if it doesn't take a lot of energy to remove those electrons, as you can kind of see that it increases quite a bit, that means that if it has a low enthalpy, meaning it doesn't take a lot of energy to remove it. So if there's a large jump in the values, this means that the jump means that it's due to the fact that the core electrons are closer to and less shielded from the nucleus, and therefore requires energy to remove them if there's a big noticeable jump. For example, magnesium has this electron configuration, and we know that it has 2 valence electrons. You can see that there's a big jump between the second and third ionization energies, and again the 10th and 11th. That's kind of quite a big jump. This shows when electrons are being removed from a shell that is closer to the nucleus. So you see it goes from 738 to 1451, so about 700, to remove the first, to remove the second, but to remove the third electron, it goes up to 6,000. There's a 6,000 whatever jump. So that means that large gap from here to here, that's kind of like, I'm just going to draw it on top of this. So this is my nucleus, 1, 2, 3. That's really ugly. So remember, it's 1, 2, then So if you're going to remove this one, then this one, that's these two right there. So those are already gone. So to remove that, if you'll notice that first second to go to the third one, it does greater enthalpy, so it takes more energy to remove it. Atomic radius of a chemical element is a measure of the size of its atoms, and it's usually the mean or typical distance from the center of the nucleus to the boundary of the surrounding electrons. It increases as you move down a column, as there are more electron shells. Atomic radius decreases as you move left to right. Electrons are being added to the same energy level, and at the same time more protons are being added to the nucleus. Increasing the number of atoms gives a higher effective nuclear charge. In other words, there's a stronger force of attraction pulling the electrons closer to the nucleus. Therefore, there is a smaller atomic radius because you have a greater number of protons pulling on electrons, and you're increasing electrons as well. Ionic radius. The trends for ionic radius are similar to the atomic radii, except that cations and anions are different from each other. Cations are always smaller than the parent atom because they have lost their valence shell. This causes them to be smaller. There's also a decrease in size because nuclear attraction is now acting on fewer electrons, so they are drawn in closer towards the nucleus. There are also fewer electron-to-electron repulsions. Anions, on the other hand, are always larger than the parent atom. Electrons are added to the same valence shell. However, there are greater electron to electron repulsions, so the ion increases in size. And notice how they are diagrams showing the ions and how they change. So why do I bring that up? Sometimes you may be asked, and we'll go over this later on, that you're going to have to draw something called a particle diagram, showing, for example, potassium chloride being put into water and it interacts with water molecules. How will that interact? How does that look? And part of being able to do that is having the correct correlation of the size of the particles within reason. Like, it's like, don't make it like so hard that you can't tell there's a difference, but don't make it kind of comically like just kind of like, okay, you're just trying to be silly. But what I'm trying to say is that cations get smaller. So if you have a sodium atom versus a sodium ion, it got smaller because you're losing the shell. If you have, let's pick one. So we have oxygen here. It gets bigger because it gains electrons, and there are greater electron to electron repulsion, so the ion is bigger. So you indicate that somehow. Electron affinity is the amount of energy involved when an electron is accepted by a gaseous atom to form a negative ion. In other words, the neutral atom's likelihood of gaining an electron. The values tend to be negative to show energy is released as electrons are added to the atoms. In general, electron affinity increases from left to right. This is caused by the filling of the valence shell of the atom. A group 17 atom releases more energy than a group 1 atom when it gains an electron, indicating that it's more stable. So it's kind of like electronegativity, but not really. A trend of decreasing electron affinity when moving down the groups might be expected. The additional electron will be entering an orbital further away. Since this electron is further away from the nucleus, it is less attracted to the nucleus and will release less energy when added. According to like all this stuff here. So this trend would apply only to group 1 atoms. Electronegativity. It is a measure of an ability to attract shared electrons. Electronegativity decreases as you move down a column, as there's a greater distance from the nucleus and more electron shielding. Electronegativity increases as you move across the periodic table, left to right. This is because the atomic radius is decreasing while the number of protons and effective nuclear charge is increasing. Fluorine is the most electronegative element. So if you notice, it says the ability to attract shared electrons. So if there is no difference in electronegativity, they are shared equally. So it's a nonpolar covalent bond. A slight difference in values means they're unequally shared. This is a polar covalent bond. Remember our tug of war from 2 years ago. Large difference in values, electrons are not shared, they are transferred, stolen, etc. That's an ionic bond. Whenever you are stating a trend, you are not explaining it. So, why does it have a large atomic radius? Because it is, because of its position on the periodic table. Don't ever do that because you will not get credit. When you're going to be looking at explaining a trend, you have to talk about the size of the number of orbitals, or increasing protons and electrons, increase shielding, increase this, decrease that. Okay? Choose the atom. So all we're doing is just choosing the atom with the higher first ionization energy, larger atomic radius, and higher electronegativity. So we're just going to choose, but I may explain just so we are aware of what's going on. So the higher first ionization energy between sodium or lithium, meaning which one will take more energy to remove the first valence electron, it will be lithium because it has less orbitals. Less orbitals. Higher first ionization energy, fluorine or oxygen, it would be fluorine because it has more protons and electrons. So therefore, there's a greater attraction of the protons to the valence electrons, to the electrons. Larger atomic radius, sodium or lithium, it would be sodium because it has one more orbital. Larger atomic radius would be oxygen because there are less protons and less electrons for the attraction of the nucleus to the valence shell. Higher electronegativity, sodium or lithium. Ability to attract an electron, it would be lithium because it has less orbitals, there's less shielding. Higher effective electronegativity, F or O. Remember we talked about, it wants to make a full valence shell. So we have to say now it has more protons and electrons than oxygen. Rank from smallest to largest atomic radius. So give yourselves a minute, try this out. Okay, so smallest to largest. So remember that if you had to recognize, are these on a period, are these on a column, all that type of stuff. So CNO. Oxygen has the most protons, has a highest atomic number, than nitrogen and carbon. So it's going to be oxygen, nitrogen, and carbon. Chlorine, chlorine, argon, potassium. Smallest to largest. So this one is also a row. So left to right. So argon, chlorine, and then potassium, smallest to largest. Beryllium, magnesium, calcium, smallest to largest. Luckily for us, it's the same order. So beryllium, magnesium, calcium. All right, gentlemen, if you have any questions, please let me know. Hit the like and subscribe. Thanks. Bye.